10 kilograms of nitrogen gas is contained in a closed rigid tank right here, surrounded by 2 kilogram water bath. It's right there. And the initial temperature of the nitrogen and water are 50 degrees C and 20 degrees C respectively. The entire unit is well insulated, so that's indicated by this thick black line here. And the nitrogen and water interact until thermal equilibrium is achieved. That means that the final temperature of the nitrogen and the final temperature of the water are the same. And the measured final temperature is given, 34.1 degrees C. We're told the water can be modeled as an incompressible substance. That's usually a pretty good assumption, with a specific heat given here. And the nitrogen is an ideal gas with constant specific heats. So we call that a perfect gas. An ideal gas with constant specific heats, we sometimes call that a perfect gas. Determine the average value of the nitrogen specific heat at constant volume. So the C sub V is what we're trying to find. So this is a first law kind of analysis, because what we have here is we're having a change in internal energy of the nitrogen and the water. There's no heat transfer going on through this insulated barrier, and the fact that we're dealing with closed rigid tanks means that there's no work being done. So all we're dealing with are just changes in internal energy ultimately. Let's go ahead and indicate what our system is. Our system is going to be the nitrogen and the water. So I'll show that as a dashed line here. I'm going to write out my first law. The change in total energy of the system is equal to the heat done or going into the system minus the work done by the system. And we'll go ahead and expand these out here. So first of all, we'll expand out the heat transfer. That's going to be 0. Now there is some heat transfer between the nitrogen and the water, but that's inside our system, so we don't worry about it. It's all happening inside. This heat transfer is across the system boundary, and since it's insulated, that's going to be 0. Same sort of thing with the work. That's going to be 0 because we're assuming that the box is rigid, so there's no change in volume. We're assuming that there are no other sources of work like paddle wheel or electrical work or anything like that. So all we're dealing with are changes in the total energy. And let's expand that one out. The change in total energy of the system is going to be the change in the internal energy plus the change in kinetic energy plus the change in potential energy of the system. But since the system isn't moving, the change in kinetic energy is going to be 0. And since it's not changing elevation, we're not getting changes in potential energy. So this will just be changes in the internal energy of the system. So let's expand that out. The change in internal energy of the system, well, the system is comprised of nitrogen and water, so we're going to have the change in internal energy of the nitrogen and the change in internal energy of the water. So I'm going to break it up into those two components. So both of these add up to be my system. And to get each of these, I'm going to expand those out in the following way. Let's start with the nitrogen. So the change in internal energy of the nitrogen will be the mass of the nitrogen times the specific heat at constant volume of the nitrogen. That's the thing I'm trying to find. Times the change in temperature of the nitrogen. So the final temperature of the nitrogen minus the initial temperature of the nitrogen. Now, in going from this step to this, I'm assuming that the nitrogen is an ideal gas with a constant specific heat. So I'll write that down in a moment, but that's the assumption, that the nitrogen is an ideal gas with constant specific heat. Now, writing down the change in the internal energy of the water, that's going to be the mass of the water times the specific heat of the water times the temperature difference in the water. And in going from here to here, I've assumed that we're dealing with an incompressible substance and one where the specific heat doesn't change with temperature. One thing to just notice that when I'm doing the incompressible model here, it's just the specific heat. There is no C sub V or C sub P, it's just specific heat. When I assume that this was an ideal gas, then the change in internal energy is related to the C sub V, okay, for an ideal gas. So let me write down those assumptions and going from this step to this step. So assuming that nitrogen is an ideal gas with constant C sub V, so that we call that a perfect gas. So that's one assumption I made, and that the water is incompressible with constant specific heat C. So those are the assumptions I used in writing out this expression here. If these specific heats weren't constant, then I would have to find it this way. So the change in internal energy of the nitrogen gas would look like the following. I would have to actually do the integral of C sub V, which would be in general a function of temperature, times dt. This would be the mass of my nitrogen out front. So it'd be the mass of the nitrogen times the integral of C sub V, which is a function of T, times dt as you go from the initial to the final temperature of the nitrogen. And similarly, if I assume that the specific heat for the water wasn't a constant, I would have to write that as the mass of the water integrating from the initial temperature of the water to the final temperature of the water times C, which would be a function of temperature times dt. So that's how I would account for the change, the specific heat variation with temperature in both of those cases. But fortunately, the specific heats are assumed constant here, so I don't have to worry about that. All right, so remember that what we're trying to solve for in this problem statement is the average value of the nitrogen's specific heat at constant volume. So what I'm going to do is just take these expressions here, plug them back into the first law, and then just solve for the C sub V. So if I do that, I'm going to get the following. The C sub V is equal to, let's see, minus mass of the water, specific heat of the water, T final of the water, minus T initial of the water, divided by mass of the nitrogen times the final mass of the nitrogen minus the initial final temperature of the nitrogen minus the initial temperature of the nitrogen. Okay, so now I'm at a point where I can start plugging in numbers. We're told that the mass of the water is 2 kilograms. The mass of the nitrogen is 10 kilograms. We're told the initial temperatures of the water and nitrogen, and the final temperature of both the nitrogen and the water is given as well. So let's write those down just to be complete. Mass of the water is 2 kilograms. Mass of the nitrogen was 10 kilograms. The initial temperature of the water was, just go back and look at it again, 20 degrees C. Initial temperature of the nitrogen was 50 degrees C. Final temperature of the water and the final temperature of the nitrogen are the same because they're in thermal equilibrium. That was the 34.1 degrees C. And then the specific heat of water, that's given to be the 4.179 kilojoules per kilogram Kelvin. All right, so we have everything we need to know, and so we can solve for the specific heat at constant volume for the nitrogen. And that comes out to be 0.741 kilojoules per kilogram Kelvin once you plug in all the numbers. Okay, so this is an application of the first law. We made use of the fact that it was an insulated container, so the heat transfer is zero. It's a rigid container, so there's no work, and there's no electrical work or anything like that. We also made use of the assumption that the nitrogen is an ideal gas with a constant specific heat at constant volume, and that the water was an incompressible substance with a constant specific heat. And then the rest of this was just doing some rearranging and plugging in numbers. Okay, we'll end the example there.